Let's find the limit of a sub n equals 2n over square root n squared plus 1. So for this one, we're just going to use the limit formula. And if I plug in, and if I let n approach infinity, I should get infinity over infinity. But you don't have to use L'Hopital's rule and all that complicated stuff. So instead what I'm going to do is multiply top and bottom by 1 over n. So the top is 2. For the bottom, I can take the 1 over n, put it inside the square root as 1 over n squared. And so I need to distribute that to n squared plus 1. I'm left with 2, and then 1 over n squared times n squared is 1, plus 1 over n squared times 1. And now, if I let n approach infinity, this is going to go to 0. And thus the limit is 2. So because the limit is finite, this sequence is going to converge. Okay, so let a sub n equal sine of 1 over n. Now if I look at this limit, we know that 1 over n, as n approaches infinity, goes to 0. So this is essentially sine of 0, which is 0. The limit is 0, therefore the sequence converges. Okay, now we're going to let a sub n be 3n squared minus n plus 4 over 2n squared plus 1. I'm going to take the limit as n approaches infinity. And for this, you can think of it as finding the horizontal asymptote, where you can ignore the negative n, the 4, and the 1, and just look at the coefficients of 3 and 2, since they're both n squared. So you would get that the limit is 3/2. If you don't like this way, what you can do also is divide everything by n squared. So in other words, multiply by 1 over n squared to the top and the bottom. So 3n squared over n squared is 3. N over n squared is 1 over n. 4 over n squared is 4 over n squared. In the denominator, you get 2 plus 1 over n squared. And so anything that's over n is going to go to 0, because the idea is that the denominator gets huge, and so your answer approaches 0. Okay, and then as you can see, we still get the same limit. And so therefore this sequence converges. Now we're going to use, or we're going to let a sub n be 1 plus negative 1 to the n all over n. And this one is interesting because the negative 1 alternates between positive and negative. So what happens? In order to solve this limit, it's good to use the squeeze theorem. So can I find a bigger and a smaller limit that will converge at the same limit? Okay, so let's find a upper and lower bound for a sub n. A good place to start is at negative 1 to the n. So we know negative 1 to the n, is negative 1, 1, negative 1, 1, etc. So it just alternates between negative 1 and positive 1. So the biggest it can be is 1. So I'm just going to replace this negative 1 to the n as 1 for the upper bound, which is really the limit as n approaches infinity of 2 over n. And for the lower bound, I'm going to pick the smaller number, which is negative 1. So that would be 1 plus negative 1 over n. 1 plus negative 1 is 0. That 0 over n is 0. So we have 0 is less than or equal to the limit as n approaches infinity of 1 plus negative 1 raised to the n over n. And that's going to be less than or equal to limit of 2 over n. Okay, so the limit as n approaches infinity for 2 over n is 0. So what we found is our sequence is bounded between two sequences that are both going to 0. So by squeeze theorem, a sub n should also go to 0. And because it's approaching 0, it converges. Okay, now let's look at a natural log of n cubed over 2n. This one, I would bring the 3 outside because a log brings the exponent in front. Okay, so this is the property that I'm talking about. If I have, let's say, ln of x to the k, you can bring out the exponent and leave everything else the same. Okay, so now this just comes down to finding the limit of 3 times ln of n over 2n, which is really infinity over infinity. So I have to use L'Hopital's rule. The derivative, and now also I'm going to pull out the 3 over 2 in front. So the derivative of ln of n is 1 over n. The derivative of 2n is just 1. So essentially this is just 1 over n. So I have 3 halves times the limit as n approaches infinity of 1 over n. That's 0. So 3 halves times 0 is 0. And therefore the limit converges, or the sequence converges. Okay, now let's look at a factorial problem. So if I have n plus 1 factorial over n factorial, I obviously want to find the limit first, but I'm going to simplify this. I'm going to leave the n factorial the same, but I can rewrite the n plus 1 factorial as n plus 1 times n minus 1, etc., which is the same thing as taking n plus 1 and multiplying it by n factorial. The n factorials are going to cancel, and so I'm left with n plus 1. Now if we take the limit as n approaches infinity of n plus 1, we know that goes to infinity, and therefore it diverges. Because in order for it to converge, it has to be finite. The limit has to be finite. Okay. Last one. Now we have a sub n is equal to n to the p over e to the n. And here we're given that p is positive. So again, we have to find the limit of this sequence. And clearly, if I plug in, or as I approach infinity for n, they're both going to approach infinity. So now I'm going to have to take the derivative here. And just to recall, if I have, let's say, the derivative, this is like x to the n, by the way. So p is a constant. So you can think of this as x to the n. Every time I take a derivative, I have to subtract 1 in the exponent and bring it down. And then to find the other derivative, you keep doing this until eventually you get x to the 0. And so what that is really n factorial times x to the 0. And so it really simplifies to n factorial. And here I'm just going to keep doing that because, you know, if I have n over e to the n, for example, I need to still do L'Hopital's rule to get it to 1 over e to the n. So I'm going to continuously do L'Hopital's rule until I have 0 in the exponent of n. So I'm going to perform this the L'Hopital's rule by whatever the exponent is. So here it's going to be p times. So we're going to use L'Hopital's rule. P times in order to get the exponent down to 0. And so really that's just going to be p factorial over e to the n. And it's just a constant over an exponential, and that's clearly going to 0. And therefore the sequence converges.